Now I will explain how to find out the second order derivative. Now here I consider a function y equal to fx, where x is an independent variable and y is dependent. Now if we differentiate y equal to fx with respect to x, then what we will get? We will get d dx of y, that is equal to d dx of fx, and you know that. And therefore we can write in this way dy dx equal to f dash x, and this derivative known as first order derivative. The dy dx and f dash x both represent first order derivative. Now if we differentiate this first order derivative once more, that means with respect to x, that is d dx of dy dx equal to d dx of f dash x, then we can write in this way d2y dx2, that is or d square y dx square equal to f double dash x, and this derivative known as second order derivative. Thus the derivative of first order derivative is called second order derivative. And if we differentiate this first order derivative dy dx with respect to x, then we will get the second order derivative. Here we mention some notation from first and second order derivative for the function y equal to fx. For first order derivative, you know, we dy dx we represent by dy dx, or another notation is y dash or y1 or dy or f dash x. And for second order derivative, the corresponding notations are for dy dx in case of first order derivative it will be dy dx2. If it is y dash for first order derivative, then it will be y double dash in second order derivative, and so on, y2 d2y f double dash x, etc. Now we will learn some problems how to find second order derivative of a function. Here are three functions and they are explicit functions. That means dependent variable y has been given explicitly in terms of the independent variable x. First function is y equal to x square plus 6x plus 5. First we need to differentiate y equal to x square plus 6x plus 5 with respect to x. That means dy dx equal to d dx of x square plus 6x plus 5. Now using the formula of derivative, that means d dx of x to the power n formula, n x to the power n minus 1, d dx of x to the power n is n x to the power n minus 1. Using that formula we get derivative of x square is 2x plus derivative of 6x is 6, and derivative of constant term 0. That means derivative of 5 is 0. Therefore resulting function is 2x plus 6. Now to find second order derivative d2y dx2, we need to differentiate 2x plus 6 once more with respect to x. That means d dx of 2x plus 6, that is equal to 2, using the same formula, that is d dx of x to the power n. Moving on to the next function y equal to cos square x. Here assume cos x, you know that, assume cos x as x. So first of all we have to use the formula of x to the power n. That means here cos square x equal to derivative of cos square x is 2 cos x into derivative of the function you imagined as x. That means derivative of cos x, that is equal to minus sin x. Total function is 2 cos x into minus sin x equal to minus sin 2x. Now second order derivative of the function, that is d2y dx2 equal to d dx of minus sin 2x, that is equal to derivative of sin x is cos x. Therefore derivative of sin 2x is cos 2x and derivative of 2x is 2. Therefore d dx of minus sin 2x equal to minus 2 cos 2x. Next the third function. is y equal to sine log x. Here imagine log x as x. Therefore first we will use the derivative of the function sine x. Derivative of sine x is cos x. Therefore here it will be cos log x into derivative of log x, that is equal to cos log x into 1 by x. Now the second order derivative d2y dx2, that is equal to d dx of cos log x into 1 by x. Here we will use d dx of u into v rule. D dx of u into v, that is equal to here u into dv dx plus v into du dx. Here cos log x, one function and another function is 1 by log x. Therefore cos log x fixed, derivative of 1 by x, that is minus 1 by x square, plus minus 1 by x fixed and derivative of cos log x minus sine log x into 1 by x, that is equal to minus 1 by x square into sine log x plus cos log x. Find d2y dx2 when y equal to log of log x. Y equal to log of log x. Now dy dx equal to d dx of log x. Now using the formula, derivative of log x is 1 by x. d dx of log of log x will be 1 by log x into d dx of log x, that means this function, that is equal to 1 by x log x. Now d2y dx2 equal to d dx of this function, that is dy dx, d dx of 1 by x log x. Now using the formula d dx of x to the power minus n, we will get minus 1 by x log x whole to the power 2 into d dx of x log x. That is equal to minus 1 by x log x whole to the power 2 into x into 1 by x plus log x into 1. Actually we used the rule d dx of u into v. That means u into derivative of v plus v into derivative of u. That is equal to minus 1 by log x by x log x whole to the power 2. Next example. If x plus y equal to e to the power x minus y, then prove that d2y dx to this one. This function is called implicit function. That means a function, in this function the dependent variable y is not expressed in terms of the independent variable x. To find out the d2y dx2, we just x plus y equal to the power x minus y, taking log from both sides of this function, log of x plus y equal to x minus y. That means we just converted this exponential form to logarithmic form. Differentiating both sides with respect to x of this function, d dx of log x plus 1 equal to d dx of x minus y. Derivative of log x is 1 by x, therefore derivative of x plus y will be 1 by x plus y into derivative of this function, that is x plus y, according to chain rule. Therefore derivative of x is 1 with respect to x plus derivative of y with respect to x is dy dx equal to derivative of x with respect to x is 1 minus derivative of y with respect to x dy dx, or taking common dy dx, we get 1 by dy dx into 1 by x plus y plus 1, that is equal to 1 minus 1 by x plus y, or dy dx equal to this one. Now d2y dx2 equal to this function, this function using the rule d dx of u by v, we get x plus y plus 1 whole square and x plus y plus 1 fixed, derivative of this function, that is x plus y minus 1 plus dy dx, minus x plus y minus 1 fixed, derivative of the function x plus y plus 1, that means 1 plus dy dx. Now that is equal to 1 plus dy dx into 2 by x plus 1 plus x plus y plus 1 whole to the power 2. And therefore the resulting the answer will be d2y dx2 equal to 4x plus y by x plus y plus 1 whole to the power 3. Here find d2y dx2 where x and y are in parametric form. That means x, y are expressed as a function of a parameter. That is here, that is theta. And we will find d2y dx2 at theta equal to pi by 2. Here x is a function of theta and y also function of theta. First of all, we differentiate x and y with respect to theta. Dx d theta equal to, therefore dx d theta equal to minus 2 sin theta plus 2 sin 2 theta, and derivative of y with respect to theta is 2 cos theta minus 2 cos 2 theta. Now to find dy dx, we can write dy dx as dy d theta divided by dx d theta. That is equal to dy d theta means 2 cos theta minus 2 cos 2 theta, and dx d theta means minus 2 sin theta plus 2 sin 2 theta. Therefore dy dx will be 2 cos theta minus 2 cos 2 theta by minus 2 sin theta plus 2 sin 2 theta. After simplification, we get dy dx equal to tan 3 theta by 2. Now we will find d2y dx2. d2y dx2 equal to ddx of dy dx. Since dy dx is a function of theta, we can write in this way: d theta of dy dx into d theta dx. That is equal to d theta of dy dx. d theta of dy dx means d theta of tan 3 theta by 2 into d theta dx. d theta dx means 1 by minus 2 sin theta plus 2 sin 2 theta. Therefore, after simplification, it will be d2y dx2 will be 3 by 8 sec cube 3 theta by 2 into cosec theta by 2. Now at theta equal to pi by 2. That means putting theta equal to pi by 2 in d2y dx2, we get 3 by 8 sec cube 3 into pi by 2 by 2, that means 3 pi by 4 into cosec pi by 4, that is equal to minus 3 by 2. Therefore, at theta equal to pi by 2, the value of d2y dx2 is minus 3 by 2.